By 2025, AI has moved from an experimental initiative to a mandatory requirement for enterprise competitiveness. Across the corporate landscape, more than 85% of organizations are now actively operating either managed or self-hosted AI environments. However, this rapid integration has exposed a massive attack surface. Security teams are now handling a surge of critical risk alerts, stemming from unauthorized shadow AI usage, dangerous drone footage, and assistance granted excessive permissions. Organizations now face an immediate operational paradox. They must deploy highly capable AI systems to maintain their market position, but doing so without structural safeguards risks exposing sensitive proprietary data. The logic of enterprise hosting changed as open-source models reached performance parity with proprietary closed-source systems. This chart visualizes the benchmark scores proving parity. On the Math 500 test, DeepSeek R1 scores 97%, outperforming O1 at 96.4%. Organizations are capitalizing on this cost-to-performance ratio, moving away from managed endpoints. Year over year, self-hosted AI adoption reached 75%. Moving away from vendor-managed APIs means the enterprise assumes total responsibility for the system. The burden of data privacy, model governance, and runtime security falls directly on internal engineering teams. Securing these self-hosted production-ready AI models requires engineering custom cognitive architectures and strict workflow controls. Basic prompt engineering is no longer sufficient. Out of the box, a large language model is entirely stateless. It treats every single interaction as a blank slate, restricted by the hard constraint of its token context window. Relying solely on context windows to manage complex tasks forces engineers to stuff entire conversation histories into a limited space. Focus on the primary task, resulting in processing errors and rapidly escalating token costs. The engineering solution is to build an agentic cognitive architecture. This approach abstracts memory and state management completely outside of the language model's direct context window. An agent cannot handle multi-step enterprise workflows without an externalized memory architecture designed to persist its operational state. This schematic outlines the two distinct tiers of memory required for a functional enterprise agent architecture. The first tier is short-term memory. This is thread-scoped state, managed via checkpointers. It persists the immediate conversation history, but remains isolated to a single workflow session. The second tier is long-term memory. This utilizes cross-thread namespace-spoke storage, allowing the system to recall information across different sessions at any time. It consists of three specific subcategories. The first is semantic memory. This manages factual data about users or concepts, updated via JSON patches or document collections to maintain accurate entity profiles. The second is episodic memory. This catalogs the agent's past experiences and actions. Engineers utilize episodic memory for few-shot prompt programming, providing specific examples of past successes to guide the model. The third is procedural memory. This contains the agent's core operational instructions, which are refined dynamically over time through meta-prompting and reflection loops. When implementing these stores, engineers must choose between writing data in the hot path for real-time updates at the cost of latency, or writing in the background using asynchronous logic. Integrating these specific memory typologies provides a static text generator with the persistent context required for long-term enterprise reasoning. Granting an agent the ability to recall data and execute actions introduces the risk of excessive agency. Fully autonomous agents might attempt irreversible tasks, like database modifications or outbound communications, without oversight. This workflow diagram shows how to mitigate excessive agency. Agent tasks must be restricted within deterministic workflows built on predictable event streams. To inject a human in the loop, the workflow tool is explicitly programmed to emit an input-required event directly into the stream, halting execution. This event is tagged with a unique waiter ID. This ensures the system tracks exactly which execution state is currently suspended. The workflow remains frozen. If the wait takes hours, the context is serialized to a database. Operations only resume when an explicit human response event is injected back into the stream. Unchecked autonomy is a direct liability. True enterprise-grade agents require these programmatic pause states to guarantee human oversight on critical actions. Internal cognitive controls must be surrounded by a resilient external security perimeter to safely deploy the agent. Traditional static and dynamic application security testing controls are insufficient here. They are built for static code and cannot effectively protect self-hosted, non-deterministic AI models. This diagram represents the specialized AI development lifecycle pipeline. Organizations must track and secure the model from raw data ingest through training, evaluation, and final deployment. The data preparation phase introduces critical vulnerabilities. Engineers must actively scan for data poisoning attempts and the accidental inclusion of plaintext secrets in the training set. During the evaluation phase, the compiled model must be actively tested against jailbreaks, prompt injections, and systemic bias before reaching production. At deployment, the primary threats shift to runtime vulnerabilities, specifically insecure plugin usage and agents operating with over-permissioned access to unsiloed enterprise data lakes. Securing this perimeter requires a bifurcated approach. Organizations must utilize specific solutions to govern everyday AI usage, while deploying separate controls to secure the homegrown AI product lifecycle. AI security is not an operational afterthought. Discovery, cataloging, and active runtime monitoring must be baked into every phase to prevent data compromise. This master schematic synthesizes the secure deployment strategy, a language model utilizing namespace memory silos, regulated by deterministic workflow controls, all wrapped inside a continuous AI SDLC perimeter. An enterprise AI agent operates as an orchestrated system of precise state management. Without these memory typologies, the system faces context collapse and begins hallucinating. Without event-driven workflow controls, the system operates with excessive, dangerous agency. Without an AI-specific runtime perimeter, the system is wholly vulnerable to data poisoning and injection exploits. As open-source foundation models reach asymptotic performance parity, the raw intelligence of the model itself is no longer a competitive differentiator. The true competitive advantage for enterprises in 2025 is the maturity of their surrounding infrastructure. The only way to deploy AI at scale is to engineer it securely from the ground up.